guys, and welcome again to this one. I'm buzzing and excited. Still a Tuesday, and yeah, the second day of the week. And yeah, we're buzzing. We're buzzing. So for this one, it's kind of a bit of an explanation, right? So I was following the EPI, that's element of programming interviews, problems one after the other, but I kind of noticed something that made me to stop, and that was the fact that I solved whenever I looked at recursion problems. That twist that goes on in recursion. I don't know if it's just me, right? But when I see recursion problems, I had a problem with it. I had like a fright towards it. If that makes sense. Not necessarily afraid of it, but like going it through loops and iterations didn't really make sense to me. And for that reason, I was like, okay, do you know what? Let me just go on a rampage, solving strictly recursion problems, and see if I'm better off on the other side. And basically, that's what I did starting from today. So from today to like subsequently, most of the problems I'm going to be solving are going to be recursion based problems. So I get into that groove of solving recursion problems. So I get into that mind frame of solving recursion problems. And yeah, and we see how it goes. So for the first one, we are going to be looking at binary possibilities. What are we looking for? We said brute force recursion. Brute force using recursion, right? Basically, we are saying when we say brute force, obviously we mean that we are iterating through every possibility to get this answer, right? And then we say we are trying to find all binary possibilities in a number range. So basically what that means is that so when we pass in 2 as an integer into the variables, we are going to be getting back all the binary possibilities. So 0 and 1, 0, 1 and 0, 0 and 0, 1 and 1. So just as I highlighted to here, right? So that's the idea of what we want this to do. And it's clearly a recursion problem because there are multiple iterations and multiple calls of a specific function for to build up something. So yeah. So let's see how we solve this. So we take it that the binary possibilities function is instantiated and we pass in the value of our integer, right? That's our first stride. Then we take in result as the value that will hold every of our possibilities, and already this tells us that this is an O of n space complexity. Then we go down, we call our backtracking function that takes in an index and a current list. What does that do? We'll see subsequently. Then we call our base case, right? And that's one thing I learned immediately. The first thing I learned with recursion problems is that there's always a base case. What's a base case in a nutshell? A base case in a nutshell is like the the place where the recursion gets to and is halted and is forced, to make to return back, or basically is halted so that the process can end, so it doesn't run perpetually, right? So we always have that in a recursion problem. So I began to see that pattern immediately, that there's always a base case, and then after a base case comes a recursive, or I think I'm the one that calls it is the recursive case, right? So basically, this is where we do our function manipulation that would help us, because what recursion does in a nutshell is what it breaks a problem down into smaller instances of that problem and then calls it again, right? And we'll see this in other problems when we begin to develop this skill as we go, or being able to see a problem and seeing that this is a recursion problem just by looking at it, and then being able to now see how we manipulate and get the solution. So basically we call a current value as 0, and then we say while that current value is less than 2, right? What do we want to do? We want to say current value dot append. I don't want this video to be too long, but I wanted to do this so that we get a clear understanding of what we do, right? The way we are going to be making appendings so that it doesn't get confusing. So but yeah, we call current list dot append, Let's recall that our current list is what we passed in here, and that was interpreted as an empty list, and we have our index at 0. So basically, we come here, we see sorry. So we come here, we see current list data pen, current value, blah blah blah, and yeah, that's me trying to gather my thoughts. So backtracking, then we look at backtracking, and we call the backtracking function again. Basically, what do? We just created the current list dot append, and we passed in the value of 0, which is the value that was initially there. We passed in that value, and then we call the backtracking function again, and then we increase the index and pass in the current value that we just passed 0 inside. Now we could see that a reduction is happening here. We are changing the values of the function and then calling it again, right? So basically now what we have in here in our current is 0, right? And then we would say, okay, current is passed in. Now when we call backtracking again, we realize that we are coming from the base case again. We check the base case. If length of the current list, right, which is right now at 1, is equals to n is 2. So basically we skip that base case because that if statement is not satisfied, or that if condition is not satisfied, and we come to this current. Now we coming to this current, this guy is still 0 while it's still less than 2, and then we call append again, appending 0 here. So we have 0 here, and we go backtracking again. Now when we call backtracking into the next index is now at what? +1, and that means it's now at 2. That means we're passing into here. The current list is now the same, is now has a length of 2, and n is now 2 as well. Now we this base case is satisfied, and we pass that guy, and then we call result, and now we append a copy. Why? I think you can. It's another good place for you to stop and maybe reason about it, and maybe drop the answers in the answer in the comment section. But yeah, to move on, right? We drop a copy of the current list because we want a snapshot. Obviously, in memory, basically what we have are pointers, right? Pointing to specific places, and And the reason for us to do this is because we want our result pointing just to a copy of the current list. Because if we don't do that, every other iteration or every other so let's say we append without a copy, right? What will happen? We would come back here and pop, and basically every change or mutation to the current list would also be mutated in the copy that is, or in the nose copy, because it's not a copy, right? It's an appending. So what we thought we copied to the result list will be pointing straight at the current list. So whatever happens to the current list will still be happening to whatever we put in the result. So basically we would have something like this, that at the latter end, where we would have the result value. Sorry, my vim practice, I need to do that. So basically we'll have something like this. We will have something like this comma this. So the amount of this thing, because all of them would be appended, but all of them will point at the same current list, because at the end of this iteration we will have that our current list will still come back to being nothing, because we must have popped out everything from it for us to uh, end the sequence basically. And that is what we would have if we don't tackle if we don't copy. So basically that's the reason for copying here. Right now, moving on, we copy here, and basically now we have this. So after passing this whole line, we tend to what? Return. So we return our value. We return to the last backtracking uh, this thing. That's the last recursion case, where we had 0 and this thing. And what do? We pop basically from the current list. So the current list would have one less value here, and then we'll make current value 1. And because the while loop says that the condition in line 19 is that if it is less than 2, we should continue our we continue calling this function, this code block. Basically, we would come here again and append current value. That will give us a value of 1 here, and when we go in again into the backtracking function, that will get us back to the base case. That will get us back to the base case, and the base case will here will now have obviously 1, right? And then we'll do that again, and once we have 1 now, we'll come back to uh, the pop. What we do? We'll pop the value of 1, we make it 2. Now our while loop stops. What do we do? Remember, this now is the second backtracking loop or base case or recursive case. So we'll go back to the first, we'll pop here. Now our value here becomes what? Becomes 1. Now the while loop has ended. We go back to the last case, we pop again, the 0 goes as well, and then um yeah, we add value of 1. Now our 0 now becomes 1. Now we go through that process again. 0 0 gets popped into results, we remove it, get 1 into results, and we remove it and remove it and remove it. This becomes 2, the sequence ends, and yeah, we will now have a bunch of empty distance. So had it been with the weren't copying, all four of our appendings would probably be 0, and would probably be an empty array. Not probably, would definitely be an empty array. And yeah, and then we'll come here and return our results. And basically that's it in a nutshell. So yeah, I think I'm going to be doing a lot of editing on this one. But I'm very excited to put this out. See you guys on the next one. Bye. Ciao. Muchas gracias. Auf Wiedersehen. Tschüss.